Students, this is the lecture number 7 in polynuclear hydrocarbon. In this lecture we are going to discuss introduction of phenanthrenes, nomenclature and isomerism in phenanthrenes, resonance and orbital structure of phenanthrenes, and in last the various method of synthesis of phenanthrenes. So first of all we can start with the introductions. Phenanthrene is a polycyclic aromatic hydrocarbon like anthracene and naphthalene. In this case it is composed of 3 fused benzene ring and which take its name from 2 terms, phenyl and anthracenes. Phenanthrene is isomeric with anthracene and it is also present along with anthracene in green oil of coal tar distillations. The phenanthrene is more important as compared to the anthracene because its skeleton is present in a number of natural products such as alkaloids, steroids, bile acids and sex hormones. So it is the simple introductions. Then come to the nomenclatures. In case of phenanthrenes, there are total number of 14 carbon atom, but the substitutions and disubstitution will occur only from carbon number 1 to 10. And in this case, all the carbon atom and hydrogen atom attached to this carbon are not identicals. So there are 5 set of equivalent pair of carbon atoms. Here we numbered these carbon 1, 2, 3, 4, 5, 6, 7, 8 and these are 9 and 10. Similarly in this way 1, 2, 3, 4, 5, 6, 7, 8 and 9 and 10s. If in this way, then it is number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10s. And it is alpha, beta, gamma, delta, and it is similar alpha, beta, gamma, delta, and these are epsilons. So there are 5 equivalent pair of the carbon atoms. If we can see this one and this one. So this one is the alpha set and it is the carbon number 1 and 8. Similarly, the beta carbon, this one and this one, it is the carbon number 2 and carbon number 7s. Then gamma, this one and this one, this is the carbon number 3 and 6. Then delta, it is the carbon number 4 and 5, and last is the epsilons, these 2, and it is the carbon number 9 and 10s. So these are the different carbons. If the mono substitution will occur in case of phenanthrenes, then it will give 5 isomeric forms in case of mono substitutions. and it will occur at carbon number 1, 2, 3, 4 and 9. And if the dye substitution will occur, then it will form near about 25 dye substituted isomers. So it is all about the possibilities of the isomerism in case of phenanthrenes and its nomenclatures. Next is resonance structure of phenanthrenes. It is comprises of 5 hybridized structures with resonance energy that is equal to 387 kilojoule per moles. So let us see its various resonating structures. This one is the structure number 1. Now this pi bond, it will shift toward this sides, and this pi bond, it will shift toward this side, and same time this pi bond, it will shift toward this side. So we are getting this structure number 2. Then in the next structure, this pi bond, it will shift toward this side, and this pi bond, it will shift toward this side, and this pi bond, it will shift toward this side. So this structure number 3 will get formed. In the next structures, this pi bond, it will shift toward this side, and this pi bond shift toward this side, and this pi bond, it will shift toward this side, and the structure number 4 will get formed. In last, this pi bond, it will shift toward this sides, and this pi bond, it will shift toward this sides, and this pi bond shift toward this side, and we are having this structure number 5. So these are the 5 resonance hybridized structure of the phenanthrenes, and the resonance energy that is 387 kilojoule per moles. The resonance energy of phenanthrene, that is near about 36 kilojoule per mole, higher as comparison to the anthracene. Anthracene having this value 351 kilojoule per moles, and this is mainly due to an additional resonating structure in the phenanthrenes. Then next is fraction of double bond character in phenanthrenes. So in case of phenanthrenes, the bond between carbon number 9 and carbon number 10, it has a maximum double bond character near about 4/5, which means near about 80%. And it can simply implies that the carbon number 9 and 10 bond is the most reactive in phenanthrene, and it will undergo various addition reaction readily similar to the ethylenic bond, double bond. Then next is orbital structure of phenanthrenes. It is a planar molecule which is similar to the anthracenes. It will comprises of 14 carbon atom, and all the carbon atoms are sp2 hybrid. So let us see how the hybridization will occur in case of phenanthrenes. We know that the atomic number of carbon, that is 6, so it will having this electronic configuration, and the valence shell of carbon having the 4 electrons. So in ground state, it will having 2 electron in 2 s orbitals and 2 electron in 2p orbitals. So the hybridization will occur in the excited state. So in this case, the one of the electron from 2s orbital, it can shift it to the 2p orbital. So this one is the electronic configuration in the excited states. And finally, these 3 orbital, it will undergo sp2 hybridizations in case of phenanthrene. So it will having 1 unhybridized orbital. So in case of phenathrenes, the carbon, each carbon that is bonded with another carbons, it will having 3 sigma bonds, 2 are with carbon and 1 that is with the hydrogens. So there are total number of carbon, that is 14. So all the 14 carbon that will having one unhybridized p orbital with 1 electron, and finally these one unhybridized p orbitals, they will undergo side-wise overlapping below or above the plane to form the rings. So there are total 14 electrons in case of phenathrenes, and it is accordance with Hacker rules, or we can say that phenathrenes is aromatic in characters. So it is all about the orbital structure of the phenathrenes. Then come to the method of synthesis of phenathrenes. In this case we can discuss Pschorr synthesis, Haworth synthesis and Kessar synthesis. So let us first discuss Pschorr synthesis. In these methods, orthonitrobenzyaldehyde is subjected to reaction with sodium phenyl acetate, and it can produce alpha phenyl orthonitrocinemic acids, and this reaction will take place in the presence of acetic anhydride, and this reaction occur according to the Perkin reactions. Then in the next step, alpha phenyl orthonitrocinemic acid that will undergo reductions with tin taken in hydrochloric acids, and it will give alpha phenyl orthoaminocinemic acids. So there is a bond formation, and in next step the reduction that will occur here. Now in the next step, this alpha phenyl orthoaminocinemic acid, it is subjected to reaction with sodium nitrate in the presence of sulfuric acid, and this reaction will occur at low temperature, and it is a diatization. So diatization that will occur at this position, and it will give this diazonium salts. In the next step, this diazonium salt, it is treated with copper and sulfuric acid mixture, then it will undergo cyclization to give phenyl 9-carboxylic acids. In last, this phenyl 9-carboxylic acids, it is heated to undergo decarboxylations. It can remove this CO2, and finally it will change into the phenathrenes. So it is all about Pschorr synthesis of phenathrenes. Then next is Haworth synthesis. This method involves Friedel-Crafts reaction of naphthalene to get a mixture of 2 isomeric keto acids. So let us see these reactions. Naphthalene and succinic anhydride in the presence of anhydric aluminium trichlorides. It will form these 2 isomers of keto acid. The first one, that is beta 1 naphthyl propanoic acid. In this case, the substitution will occur at carbon number 1, and second one, that is beta 2 naphthyl propanoic acid. In this case, substitution will occur on carbon number 2. So these are the 2 keto acids. Then simultaneously, these 2 keto acids, they will undergo Clemenson reductions in the presence of zinc, mercury and HCl mixture, and the reduction will occur at these positions, and it will give gamma 1 naphthyl butyric acids, and in this case gamma 2-naphthyl butyric acids. Then further, these two isomers, they are treated with either hydrofluoric acids or either with sulfuric acids, and it will undergo cyclizations to give 1 keto 2,3,4 trihydrophenathrenes, and in this case 4 keto 2,3,4 trihydrophenathrenes. So this cyclic product will get formed from these two isomers. Then finally, these two isomers, they will further undergo Clemenson reductions with the help of zinc mercury and hydrochloric acid, and reduction will occur at the center, and it will give a single product, that is 1,2,3 tetrahydrophenathrenes. In last, this 1,2,3,4 tetrahydrophenathrenes, it will undergo dehydrogenations with the help of palladium carbon at 573 Kelvin, and it will give the final product, that is the phenanthrene. So it is the Haworth synthesis of phenanthrenes. Then last is the Kessar synthesis. This reaction is the modification of the Pschorr synthesis, and in this method cinnamic acid derivative is converted into anthracene derivative through benzene mechanism. So this one is the alpha paramethoxyphenyl orthochlorocinamic acid, and it is treated with potassiumide taken in liquid ammonia. So it can lose this Cl plus here, and these two electrons, it will take part in the bond formation. So this benzyl intermediate will get formed first, and it is highly unstable. Then this highly unstable benzene intermediate, it will undergo cyclizations to give the final product, that is 3-methoxyphenathrenes 10 carboxylic acid. So this final product formed, it is the derivative of the phenanthrenes.